In previous examples, although one could create an output file with multiple radiological species, the dose computations were limited to a single species using the plotting program conversion factor. In this section, we will use the post-processing program con2rem to compute doses for a more realistic multi-radionuclide emission scenario. In addition to the dose_cemit script and WRF meteorology file, the activity.txt file is also required for this simulation. The use of this file implies a constant emission rate. Time-varying emissions will be addressed in the next section. The activity file lists the top 10 radionuclides and their maximum emission rate during the initial phase of the Fukushima accident. The con2rem program reads a unit source high-split concentration file and the activity.txt file that defines each radionuclide to be included in the dose calculation. Con2rem supports two high-split generated computational species, a generic particulate radionuclide, for short called rnuc, and a non-depositing noble gas labeled N-gas. Dose is computed for each defined radionuclide using either the rnuc or N-gas specifications. The dose is defined as the sum of the product of the emissions, dose conversion factor, dispersion and deposition coefficients over all radionuclides. Comparing the contents of activity.txt with the previous cfactors.txt file, you will find that the single emission rate value in activity.txt is the maximum rate found in the cfactors file. Therefore, the subsequent dose calculation will represent the maximum possible dose, not the most realistic option. One can, for example, replace the emission values in activity.txt with their average values. However, due to the variability in wind direction during this period, this approach also may not be very realistic. A better example using time-varying emissions will be presented in the next section. Examining the script in more detail, notice that in the setup.config namelist file, we define the variable maxdim equal 2, which means that both pollutants, N-gas and rnuc, will be assigned to the same computational particle. This approach reduces the particle number requirements because the default value of 1 would mean that we would emit 1,250 rnuc particles per hour and 1,250 N-gas particles per hour. Combining them on one particle is acceptable as long as both species have the same atmospheric transport pathway. For instance, you do not want to combine a species with a large gravitational settling velocity and a gas on the same computational particle. The two pollutants, a gas and a small particle, are defined in the control file both with a unit emission for the duration of the simulation. The gas is assumed to be a noble gas with no wet or dry deposition. Execute the script after the model simulation has completed. The post-processing steps are a bit different than before. Note that only one simulation was conducted for the entire period with no differentiation of emission times. This corresponds with the single emission rate defined in the activity.txt file. In the first step, the CONTAREM program matches individual radionuclides to the high-split computational species, N-gas or R-nuc. But only N-gas needs to be defined. All others are assumed to be R-nuc, a particulate. Because the match is done automatically, if the activity.txt file shows that a species has a ground-shine conversion factor of 0, it is assumed to be a noble gas and matched to the N-gas computation. There is no other way for the CONTAREM program to know which computational species represent noble gases, because the deposition field may be missing or legitimately 0. The other CONTAREM option, D1, computes the average dose over the 3-hour output period rather than decaying the value to the end of the time period. Also, this program does not have a fission stop time option, but instead the X66 parameter extends the decay time from the model simulation start time on the 14th at 00Z back 66 hours to the fission stop time 06Z of March 11th. The other two options, F and P, can be used to select the emission column if multiple emission options were available in the activity file. For instance, F1P1 would select column 1, F1P2 column 2, F2P1 column 3, and F2P2 column 4. In the second post-processing step, const sum, the ground shine, that is deposition at level 0, and the cloud shine, air concentration levels 0 to 100, those dose values are added together each time into a combined total dose output file. In the third and last post-processing step, con AVG PD, con averaging period, the 3-hourly dose values are summed together to obtain a total dose and written to the file as a single output time, covering the specified averaging time. The remaining graphics processing is similar, but we have no measured dose data at Tokai to compare with the model predictions. However, one can see that this possibly unrealistic maximum emission scenario, there are large regions where the dose exceeds 1 rem. In this high-split radiological configuration, a continuous unit source dispersion deposition calculation with two computational species, one representing a small particle and the other a noble gas, were run for a multi-day period of interest. Post-processing programs were used to assign each computational species to multiple radionuclides, each with its own emission rate, decay, and dose factors, to compute the total dose. In the next section, the multi-radionuclide dose calculation will be expanded to account for a time-varying emission rate.